This is an airfoil. When it moves through the air, it produces lift, which is very cool because it allows us to fly. The chord line goes from the leading edge to the trailing edge. When the chord line is aligned with the moving air, the angle of attack is 0. Pointing the wing up is positive angle of attack, which makes positive lift, which makes sense. We use the Greek letter alpha for the angle of attack and C sub L for the coefficient of lift. Even when the angle of attack is 0, the airfoil still produces lift because of its shape. When we change the angle of attack, the lift changes, according to this plot. If you decrease the angle of attack far enough, you hit a point at which no lift is produced. This is called alpha zero lift. We typically don't spend much time there because a wing producing no lift has lost sight of its purpose in life and is behaving more like a rock. The lift curve is pretty much linear up until the airfoil stalls. The slope of this line is CL sub alpha, and it depends on the shape of the airfoil. If you aren't sure what CL sub alpha is for your airfoil, you can probably assume 2 pi per radian or 0.110 per degree. That's the theoretical value for a thin airfoil. The lift coefficient is then CL alpha times alpha minus alpha zero lift. It's the equation for a line, if you remember algebra. If you don't know algebra, this could be rough, but I believe in you. Throw a comment below so I'll know you're watching and I'll see what I can do. When the angle of attack gets large, the lift drops off rapidly and the lift curve stops being linear. This is called stall. We will have to deal with stall eventually, but like the zero lift airfoil, the stalling airfoil has also lost sight of its purpose in life. Unless you're practicing stalls just about to touch down on landing or doing something wrong, we avoid stalling. So let's just put a pin in that for now.